Yeah, welcome to the session. Some quick flags up front. I'm very happy to make this interactive. So at any point, if you want to ask questions or have clarifications on anything I say, just put up your hand or the equivalent for Zoom rooms. So yeah, don't hesitate to do that. I imagine there will also be time in the end for more discussion, but yeah. Cool. So today, very quickly, some background on me. So I run the principles for intelligent behavior in biological and social systems project. You can check out the website we're sort of interested in, and I'll talk about related things here and sort of studying how intelligent behavior manifests in different types of systems, including like the sort of natural systems that we do are able to study and see what we can learn about intelligent systems sort of in general in ways that might translate or hopefully translate to insights that are relevant to alignment questions. And I'm also a research affiliate with the Alignment of Complex Systems group, which is an alignment research group placed in Prague and sort of interested in sort of complex systems angle on AI alignment questions. And yeah, very briefly, my background is maybe primarily in philosophy, although actually my undergrad is in international relations and like political sciences and history and stuff like that. So like pretty interdisciplinary, have engaged a bunch with complexity sciences, which I'm saying to like give you sort of some flags about the sort of like intellectual perspectives or epistemic perspectives I'm coming from with some of these observations that I'll be sharing with you. And then yeah, very quick sort of like overarching flag for like what the motivations for this talk is. So this talk will be in some sense sort of like could be categorized as like philosophy of science for alignment. And you might, I imagine some of you are like, well, but I want to sort of just concretely make progress on alignment proposals and like figuring out what the problem here is and what the risks are and how to solve them. And I'm like very much on board with that. I also believe that it is important to, from time to time, ask these philosophy of science or epistemology questions. And sort of the main reason for that is like the thing that is sort of exciting about science is that it promises to be the sort of like method of interacting with the world around us and of reasoning that helps us to, or that allows us to make systematic progress. So rather than getting lucky with figuring out things about the world or like not being sure whether we're actually making progress, like the promise here is that if we just apply this sort of method, this sort of reasoning, we will, even if slowly, make systematic progress towards understanding things better. And I also want that to be the case for the sort of alignment research we're doing. So I think occasionally asking, are we asking the right sort of questions? Are the assumptions we are using justified? What actually is all going into how we're reasoning about this problem at the moment, I think is healthy for an epistemic community to do to some extent. But obviously this is sort of like a thing at the side, and that should be in conversation with the like science and engineering efforts. But that's sort of the overarching motivation that I often experience. I'm like, well, I want to make sure we're like working on or making progress on the problem we think we're making progress on, or not on something else. And from that perspective, I think we can then sometimes sort of notice and then hopefully come to understand and address certain epistemic challenges, in particular epistemic challenges that seem particular to the problem of AI alignment. And this talk basically comes in 3 parts. And these 3 parts are sort of like addressing different types of epistemic challenges I believe we find in alignment research. Very, very quickly, so like the first problem we are finding is what I call the epistemic access problem. I'll say more about this in a second, and I'll say some words about like, cool, like what are ways we might be able to deal with this problem insofar as we're actually facing this. The second problem, this will need some more explanation in a bit, but I'm claiming that there's a problem that like a novel epistemic problem you're facing when we study artificial systems in particular. And by artificial systems, I mean systems that have been designed. They're like the product of a design process. And for some reason, this makes them like interestingly and importantly different than systems that have maybe like naturally evolved or things like that. And I'm gonna try in the second part to like illuminate that a bit more, and again raise, okay, like how do we then deal with these sort of novel questions or challenges that we find. And then this third type of challenge I think we find, and again, not all of them are sort of exclusive to alignment, but I think they're important for alignment, is various problems of complexity. So I think at the end of the day, we're studying very complex problems here, and doing science well on complex phenomena is really hard. As a scientific community overall, you have actually, it's like relatively novel that we've even started to have the sort of methodologies and scientific tools to tackle complex phenomena at all. So we are still, in some sense, relatively early days in getting good methodologies for doing that. But I'm just gonna be highlighting just a few challenges we might be running into, and also hope to illuminate how they relate concretely to like things in alignment, and how we might be mistaken about things if we're not paying attention to these sort of things. So that's the very high level arc of what we'll do. I wanna flag it's gonna be potentially pretty dense, depending on a bit like your prior knowledge on these different topics. But I'm assuming, or I'm aware that like people come in with like pretty different backgrounds, working on the main chunk of their time on pretty different problems within alignment. So really do not hesitate to like slow me down, or like ask, or like maybe ask me to like paraphrase or summarize bits again. My expectation is that this will be pretty dense, but I hope still like everyone might get different bits, and even if you're not taking away all of it, I hope everyone will be able to take away some bits of it. So that's preamble, and yeah, then I'm just gonna jump into the first bit. So the first part is about the problem of epistemic access. What do I mean by epistemic access? So basically, I mean that the way that science and engineering typically make systematic progress importantly relies on empiricism. So importantly relies on things like trial and error in engineering, and on like the scientific method and experimentation. And you have a hypothesis, and then you like basically try to like run it against reality and see how reality kicks back. And that's sort of like the fuel that allows you to make progress, according to the scientific method in general. And now, in the case of AI alignment, the problem here is that in some important sense, we are trying to study a system that doesn't exist yet. And there's some nuance here. Some of you might be very worried about existing systems already, or you might think this is like very close, or that the systems you're most worried about will look very similar to the systems we have today. And like, I grant you all that nuance, but I think there's still a very important sense in which it is not the same as studying a human brain, which we have access to, studying animal behavior, studying like physical objects that we do have access to. And again, like other domains of science face different degrees and different types of difficulties of epistemic access too. So like this in our case is something around non-existence. So like the thing is in the future, and how do we study that? But it can also just be extremely costly to like make the sort of experimental tests that would help you differentiate between different hypotheses. Or in like sort of the like complex social phenomena, there's a lot of like co-founders going on, so it can just be like really hard to like actually get the sort of clear empirical data out that you want. So empirical access is a challenge in the philosophy of science in general, but how does it sort of manifest in the case of AI alignment? And so I think this is like pretty well, so like one way I like to think about this is that there's different types of alignment research that is happening, and there's very many different ways one can categorize them, and this is like only one way of categorizing them, not the only or the correct way. But to illustrate what I want to point at, I think it's a useful way. So I'm going to suggest that there's like broadly three main epistemic strategies that people have started to adopt in order to make progress towards understanding things about future AI systems and aligning them, despite this epistemic access problem. The first one, I named this tinkering. What I'm referring to is really sort of like most of the largely prosaic technical ML safety research. And what I want to point out is that this type of research basically makes the following assumption. It says that future AI systems, so like the sort of AI systems in the future that we're most worried about or most interested in, they will look a little bit, or to some extent, like current ML systems. And given that, us working on trying to understand current ML systems, trying to like understand ways in which they could become risky or unsafe, or on finding ways in which they could be safe. Those insights are interesting and will generalize, at least to some degree, to the sort of systems we're most interested in. Another epistemic strategy that exists is sort of like, at least what maybe used to be well described as like MIRI style agent foundation research. I think that is like now a bit of a misnomer, but the basic idea here for this type of research is that we want to say something like the future AI systems will look a bit like idealized rational agents. There will be so powerful, so much optimization power, so much compute that it's like it's pretty valid to roughly equate them to acting like idealized rational agents. And given that, studying decision theory, studying formal epistemology, using all these sort of like idealized methods that involve a lot of math, etc., those are valid ways to understand the sort of system we're interested in, and in particular, understanding the ways in which such an idealized rational agent could become unsafe, or what it would have to look like for such an idealized rational agent to be safe. Those insights, again, will generalize to the thing that we are ultimately interested in. So that's the second strategy. And then there's a third strategy, which says something like future AI systems will be governed more or less or by some of the same principles as existing intelligent systems are governed. So there are sort of underlying principles of what it is to exhibit intelligent behavior that we can already see and study in currently existing intelligent systems. And those will, to some extent, be the same principles that govern the future AI systems we're interested in. And again, this is why studying these currently existing systems gives us insight that can generalize in ways that is interesting to us. And just sort of to summarize this again, so like basically what's happening here is that each of these systems that I'm like flagging here in red, those are systems we do have better epistemic access to. So current ML systems are things that exist and we can probe and do empiricism on. Rational agents, we have like formalisms about what we mean by this. So it's like well-defined, so we can study this. And existing intelligent systems, again, we have empirical access to. And then we use this sort of this red thing that I'm indicating there. We use this thing to sort of fill in the gap that we are facing with like trying to understand the actual sort of system we are interested in. So like each of these strategies relies on a different assumption to bridge this gap that is creating the epistemic access problem in the first place. And why is this interesting to us? So like I'm gonna do a short sort of like detour and then like come back to this question for why this is interesting or what we can gain from this. I wanna ask a question. Wait, we're often interested in asking, what should we expect to be true about future AI systems? And interestingly, many different people have pretty different intuitions about this. And we can ask what's going on here and like, who is right or how could we tell who is more right? I think the thing that is going on here importantly is that people will, when they like you sort of use their intuitions to reason about this question of future AI systems, they will rely on different proxies to reason. So they will do things roughly like, well, the sort of AGI that I'm talking about here, we basically can think of this as a super smart human, or we can basically think of it as a powerful rational agent specifically, or we can think of it like current ML but better, or we can think of it like statistics but like just really, 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 really powerful. Or maybe it's just equivalent to like automating all of labor, or evolution but on steroids. So like markets but like much more optimization power going into markets. And like what I'm trying to, there's various other things we could generate here. What I'm trying to point at is those are things those proxies are things we understand to some extent and we have intuitions about. And we then say, well, maybe the future system will look a bit like that. And this is where we're gaining our intuitions from. And this is interesting because I think the most important point here is something like, none of these proxies is the correct proxy because they're all proxies, because the thing we're talking about doesn't exist yet. So it's not really which one is the correct proxy. There is more subtle questions we can ask that are interesting, namely, like some features about humans, but more powerful, like maybe some of these features do generalize and some features about rational agents, but more powerful generalize. But the question is which one? And so what it allows us when we start to notice we're like doing proxy-based reasoning here is, for one, we now are able to actually do rational reasoning, rational argumentation with each other about those proxies. Which proxies are better and worse? When are they better and worse? How do they apply? When do they sort of start to break as good proxies? Which we are not really able to do when we try to directly reason about AGI, because none of us has access to that. And the second thing this grants us is that we can start to sort of like question these assumptions, like actually make them explicit. I think when you look at current like discourse, and people disagree heavily maybe on like what capabilities there will be, or how quickly, or like what we should be worried about. Sometimes it feels a bit like there's a lack of traction to even understand why people disagree so much, or like it feels like you can present arguments and there's not much updating happening. Understanding or like modeling what proxies they're using or what proxies inform their reasoning, I think can often grant you more traction on sort of rational discourse. And the other thing is that we are able to do what I'm going to call triangulation, namely, so like if none of the proxies is the correct one, maybe when we use a bunch of them and we find properties that each of the proxy predicts, well, we can be more confident about this property. So again, the idea is this thing we're interested in future AI systems is epistemically underpowered, importantly underpowered. How do we still make progress? We can make progress by triangulating different perspectives and finding predictions that have sort of epistemic robustness, in the sense of different independent perspective predicting the same thing, gives us more confidence that this thing is something we should be paying attention to. There's two citations I want to give you from a book by Wimsatt that I'll cite again later on in this talk, that I think illustrate this pretty well. So he says, fallible thinkers, and this describes us because we are bounded and the world is pretty complex, so we are importantly fallible as thinkers, should avoid long serial chains of reasoning, because if you have long chains of reasoning, even if you hope they're deductive, thus like truth preserving, those chains will always fail at the weakest link, and chains of reasoning, importantly, only most probably fail at these weakest links. So like if you, the point here is that if you have an argument that relies on a long chain of reasoning, the probability of that argument being true is not higher than your weakest link in the argument. On the other hand, and this is the second bit here, he says, with independent alternative ways of deriving a result, the result is always surer than its weakest derivation. So the alternative to the serial chain is to have different perspectives that importantly have to be sort of like independent or not co-founded. And now like the prediction or the understanding you gain about the thing you're trying to understand, it will actually be necessarily stronger than your weakest perspective, because you're like adding on. So that's the intuition for like why triangulation leads to epistemic robustness. The very important remark here is that you're only actually triangulating and gaining epistemic robustness if the different perspectives you're adding on are sufficiently independent. And there are various examples in the philosophy of science, history of science, where we sort of thought we're like we're making different modeling choices and all of them predict a certain thing. But then later on realizing actually they all were relying on a given assumption that we're biasing the results in one direction. So we weren't actually getting that much robustness. So like Wimsatt in the book, actually, one example he gives is on the study of like group selection in evolutionary theory, and given the example of how many models and like work that has been done was sort of like suggesting, or like the results were suggesting that group selection isn't having much effect. And then later on results came in, more empirical results suggesting there is actually seems to be a bunch going on at the like group selection level. And then he has a paper, I can refer you to it if you want, that like details out in quite a lot of technical detail why the different models that were suggesting group selection wasn't doing much work, were importantly relying on certain assumptions that were biasing the results in the same direction, and thus not independent, and thus sort of generating only a pseudo robustness. So this is important to notice, and this is like where really the hard scientific work comes in. where we have to like critique each other and like problematize iteratively proposals. But still, I think it's worth trying to aspire towards epistemic robustness via triangulation. Just quickly, like, how is this relevant in the alignment context? I think the two main areas of relevance here is one, the question of predicting properties of future AI systems. And I've talked a bunch about this already. I think I'm not going to reiterate that. I think a similar thing applies to understanding the risk landscape, right? So there's like, one thing where I can tell you a very specific deductive sort of like logical argument about how exactly a catastrophic risk scenario could unfold. That's one way of thinking about the risk scenario. Or you could sort of ask, on the different assumptions for like what sort of systems the details of it might look like, we tend to see certain sort of risk factors or risk drivers or like risk phenomena. And if we see them from a bunch of directions, again, through a bunch of lenses, that should, again, give us more robustness in our beliefs about understanding the landscape correctly, which I think is very important. I think one way of failing at alignment is if there's like certain like risk scenarios that we have blind spots over, that we sort of might be unable to like properly see or appreciate through the current epistemic lens we're using. And if that's the case, we're like obviously in a less good position to defend against them. So again, like taking different lenses on the risk landscape might help with sort of the blind spot intuition as well. There's one more way one can think about what I've been saying as well, which is this notion of epistemic bets and epistemic portfolio. So like the thing want to say here is that I earlier talked about the different epistemic strategies. And I think one way of thinking about these strategies is in form of bets. So rather than being like, which epistemic strategy do I think is the correct one for us to figure out this problem, I think a more reasonable way of thinking about this is that actually each of these strategies represents a bet. It uses a different assumption, and we can't know for sure whether this assumption is valid. If it is valid, this means this strategy is making systematic progress. If it's not valid, it is not. So what we now want is to have a portfolio of bets, which we can be more confident over. Again, which like buys us like epistemic robustness in this sense. I think this is basically, I'm saying the same thing again, just in a different notion. And the reason I think this is like an interesting or useful notion often is that now you can start asking, what should our portfolio look like? And importantly, what should it look like at different levels of organization? So I think the answer, what should an epistemic portfolio look like, is a different one for an individual researcher, or a different one for a research group, and a very different one, again, for sort of like a specific epistemic community in a more large sense. So yeah, I'm definitely not saying that like each of you should try within your own research agendas, maximize perspectives and different epistemic strategies. I think it's entirely valid for you to be like, look, I'm just gonna buy this specific bet. This is the assumption I'm making, and like if this assumption holds, I believe this is why my personal research agenda would mean we were making progress. But I think that's often is like the correct or a good call, but I also think you still gain something when you know which assumptions you're making. Conditional on which assumptions is your research agenda, promising research agenda. I think having conscious access to that or explicating that will help you both notice, do you actually think these assumptions are reasonable? It will allow you to potentially improve or like, calibrate your estimate about you making progress on this, on these and these questions, like under what conditions, under what assumptions, is this useful or not? Yeah, and then I do also then think it matters for us as an entire community. I think there is often tendencies, right, where like a certain approach might be sort of like get a wave of excitement, and I think the question about how much resources at the margin should flow into which approaches is a pretty nuanced one, depends on a lot of factors, but it's usually not, oh, I don't like this strategy and this is why I think no one should work on it. So yeah. Cool. Yeah, I'm gonna quickly pause, check whether there's any urgent questions right now. I'm going to give you a minute just to reflect. Well, then I'm gonna launch into the second part. I'm calling this the problem of paradigm choice. And I think the full scope of what I mean by paradigm choice will only become, or hopefully become, evident towards the end. So you'll have to bear with me a little bit. But I hope to sort of iteratively explain the full scope of this. So zooming out a little bit, I think the following observation is sort of like at the heart of this section. Namely, so like if you're interested to have something like a science of artificial intelligence, namely like actually gaining like justified knowledge about artificially intelligent systems. And I just have a quick note that I want to make here, which I think is important for what I'm trying to say, but I also want to independently say because I care about it. Artificial intelligence, and especially the way I'm using it here, I'm using it in terms of a functional equivalence. So artificial intelligence is sort of a functional notion in that what I'm referring to is artificially implemented intelligent behavior. AGI similarly is a functional equivalence, like it's an artificially implemented system such that it is like general in these ways that one has to operationalize, to be precise. What it is not, importantly, I think, is like referring to a specific paradigm, a specific technical paradigm, for example. Like AGI as a term does not necessarily refer to whether this thing is implemented as a transformer, as an RL system, various other maybe unknown symbolic AI. It's like independent of that. It's a functional equivalence. It's able to do intelligent behavior. And I think that's how I'm using the term AI or AGI here, independent from like specific technical implementation details. Okay, so we wanna have a science of AI. What does that mean? I think there's like breaks down into two bits, which both are interesting from an epistemic perspective. One is we want to understand intelligent behavior. Intelligent behavior is in itself a really interesting thing to study because it's importantly different from studying like purely physical system. The way it is different is that there's various ways of saying this. It's a bit confusing. One way I like to say this is something like there's just a bunch of feedback loops going on that mean that the system that is intelligent in virtue of, for example, carrying information about its environment in itself, being able to adapt it to its environment. And like we can say various other things that get at a similar notion here, but it is really something like this that makes an phenomena intelligent, I think in a way at least I'm interested in here, and that is different than, you know, what we would describe as Newtonian physics or something. So already intelligent behavior is kind of an interesting phenomena epistemically in terms of like how can we come to understand this. And the second thing we are trying to understand or make sense of in this context is artificial systems, like systems that are the result of design or that we have specifically designed ourselves. So going forward, when I refer to an artifact or an artificial artifact, or like what I mean always is like a designed artifact, that something that's the product of a process of design. Why is this relevant? Basically for this reason. I'm claiming that once we sort of enter the domain of the artificial, we are no longer in an epistemic domain where we are purely interested or where we're purely asking descriptive questions. So opposing artificial with natural in the domain of the natural sciences, really fundamentally what it is that we're doing is we ask questions about what is, how is the system. We are trying to describe how a natural system works. In the domain of the artificial, there's this interesting dual nature of both. There is something like understanding how an artificial system is, but also there's this interesting domain where there's a question of like what might be, like we get choice over what we are actually building, and we also additionally want trying to answer questions not only about things that already exist, but what we could come to bring into existence, and how do we reason about that sort of thing. So that's roughly what I mean here, but what might be, what is versus what might be, or descriptive versus prescriptive. And yeah, so we don't simply want to know how to build artificial, and yeah, additionally, we don't simply want to know how to build artificial intelligence systems, but we are interested to know how to build artificial intelligence systems with very specific design desiderata in mind. Namely, in our case, safety, governability, various properties you might want to have yeah. So I'm hoping I'm sort of like able to communicate this here. Yeah, we're not just trying to understand what is true about AI systems. We're trying to understand things about what is true about AI systems such that we come to be able to implement very specific versions of these systems, namely ones with specific desiderata. Giving you a bit more context, which I hope will be helpful, I'm lending a lot of language here or inspiration from a book by Herbert Simon called The Sciences of the Artificial. And again, so the artificial is that which is designed. Examples of the sciences of the artificial are things like engineering, importantly, but also like medicine, architecture, psychology, economics, administration. All of these systems clearly have this like dual nature of descriptive, prescriptive. So like in economics, right? Like when we think about the like economic agent, the rational economic agent, economics is never quite sure whether they mean this descriptively or prescriptively, or in what sense they mean it prescriptively. Clearly, we have been, I mean, to some extent moving away from this, but like very importantly, classical economics has been studying human behavior, firm behavior in terms of these like rational notions or these like idealized notions. So there's like this weird sort of like melting between, or like fuzzy boundary between descriptive and prescriptive. And that is basically true, I stipulate, for like all of these domains I'm naming here. And it's also importantly true for AI or AI alignment. And yeah, the dual nature of flagged this already. One question you might ask is like, can there be a veritable science of these sort of domains? I think this is a worthwhile citation. I'm going to quickly read this. So Simon says, the contingency of artificial phenomena has always created doubts as to whether they fall properly within the compass of science. Sometimes these doubts refer to the goal-directed character of artificial systems and the consequent difficulty of disentangling prescription from description. This seems to me not the real difficulty. The genuine problem is to show how empirical propositions can be made at all about systems that, given different circumstances, might be quite other than they are. So given different, for example, choices by people designing these systems would have ended up looking different. So now what does it mean to understand these systems in scientific terms? So that's I think the puzzle he's getting at. And the claim is that we can come to like, have a veritable science of this. Another way of at least saying some of this, and I think this is like a useful conceptual piece to have, is I think you will be all probably familiar with this notion of map, right? There's a territory, there's like the actual world out there. And what we do when we do truth seeking or science is that we're trying to create useful maps that help us navigate the territory. So map is something that we construct from investigating the world. A blueprint, in this metaphor, is what allows us to render a new bit or a bit of territory. So the blueprint, this might be literally a blueprint of building a house, and we use this epistemic artifact to create something in a territory. So the relationship between map and territory and blueprint and territory is kind of inversed. And then additionally, you can ask, what is the relationship between maps and blueprints? Like, obviously, in some obvious sense, we are relying on good maps to create good blueprints. I wouldn't be building good bridges if I had no idea about certain aspects of the physical world. At the same time, when we use blueprints to create things, we are changing the territory that we're making maps of. And at what point does this feedback loop become important to our like attempts of science and engineering? That's basically one way of putting the question I'm trying to investigate here. So quickly restating the problem, I think what we want is to be able to design AI systems with specific properties, safety, governability properties. The problem is that typically what science does, or what science is really good at, is to understand things about, like, discover what is, like, understand things the way they are. And But what we're interested to here is we're engaging in this future or design-oriented scientific enterprise. So we also have to understand things about how to orient towards what might be and how to like make these choices, or what it even means that this could come into existence versus the other thing. And I think we need a philosophy of science and an epistemology of science that helps us navigating these problems. And in trying to get towards a sufficient understanding there, we like notice particular epistemic challenges. And I'm going to now enumerate or illustrate some of these challenges in more detail. But that's sort of the basic pitch. What I mean by the sciences of the artificial is weird in some ways, and it seems important to alignment to understand some of these weirdnesses. Any questions before I dive into the next bit? Cool. Here's some peculiarities I think that arise when you study the science artificial systems. The first one is very simple, but I think it's a little bit illustrative at least. There's an important difference between forecasters and designers, right? A forecaster is someone who asks, would artifact will exist in 100 years from now? And they do some things to try to like narrow down an answer towards this question. A designer asks a very different type of question. They might, for example, ask, what artifacts do I want to exist or create in 100 years from now? And there's something interesting going on here about how they're both engaging in epistemic processes. That's the first thing I'm just going to throw out. The second thing is a bit more, is building up a bit more complexity here, but I think it actually is quite straightforward. So like one observation I think that is important to all of you is that usually there is more than one low-level implementation through which a desired function can be achieved. There's pretty simple, like a watch. If I'm interested in its function of telling the time or being able to measure the time, there's many ways I can create a designed artifact that fulfills that function. And as long as all I'm interested in is telling the time, I don't really care about which low-level implementation that is being used. And low-level implementation here just means things like sort of the like concrete theoretical and or technical sort of paradigm within which this is created. Is this an automatic watch? Is this a watch that uses the sun and shadow stuff? Is it a scent thing? Whatever. Is it a mechanical one? Cool. So several low-level implementations can render the same functional properties. And usually, or like for a long time, as long as functional equivalence is given, we're not really interested in what are the differences in low-level implementation. However, sometimes these low-level implementations come to be important. And there's something interesting in like when this happens. So Simon, in the same book as I showed before, is introducing this metaphor of like the inner and the outer environment. And I'm going to quickly cite something to hopefully illustrate this. So he says the proper functioning of an artifact, so a thing that has the product of design, is cast in terms of the relationship between the inner environment, by which he means the artifact's structure or character, its implementation details, and the outer environment, the conditions in which the artifact operates. So the functional property, like the proper functioning, like the watch telling the time, this property, this feature, this capacity is defined not purely by the system's internals, but by the sort of the proper match between the internal environment and the external environment. Why is this the case? Like, is this actually the case? Here is an example that illustrates that this is the case. A bridge, under its usual conditions of service, behaves simply as a relatively smooth level of surface on which vehicles can move. Only when it has been overloaded do we learn something about the physical properties of the materials from which it is built. So this is what I'm getting at when I say earlier here, sometimes the low-level implementation details start to be relevant. And it's sort of precisely when the proper functioning breaks, we start to actually sort of the like internal implementation details that sort of press to the surface, and we start to like learn things about them or see them, or they become relevant to us. And another good example of this, I think that is quite illustrative, is like going back to the watch, right? let's imagine I have watch A, which is just a normal automatic cheap watch, and then I have another watch B, which is specifically designed to be resistant to like really high pressures and like sort of whatever you might want to do deep sea diving, and this watch should be able to withstand those pressures. Those watches look very similar when I'm sitting here. They tell the time exactly in the same way, and I only start to notice so that the internal differences that they have so they become relevant when I'm whatever 500 meters under water and the pressure is really high and one of the watches start to break. So this is to illustrate why necessarily this functional capacity is a relational property between both the internal dynamics and the external structure. Now, I think another relevant point here is that, well, reality is really messy. There's actually a lot of detail going on in reality. And mostly, we want to be able to, ideally, we want to have to track as little of this detail as possible, because tracking detail is hard, it's costly, it's complicated, it's hard for us to do. So we want to have the sort of theories that neglect all the details that don't matter to us. But then the question really starts to become, well, which or how much detail matters? And I think this is in some sense also the question at the core of a lot of alignment research, right? We can have different sort of theories. You can have very general theories telling us things about maybe how future like scaled up LLMs work, or we have kind of much more precise theories. And the more general a theory we have, the more detail it ignores. And then the question is like, does it ignore detail that is relevant, or does it ignore detail that isn't relevant? And whether it's relevant is always relative to like something that we wanted to do. But I think that's like often the important question. And I think you can also use this like this sort of like trigger or this like prompt, potentially even also in disagreements, when you may notice you have like disagreement with someone else about like whether an approach is promising or not, whether a certain theory, whether a certain perspective is like the right way to look at what computation is, or what intelligent behavior is, or what a mind does. You can't like, probably a lot of your differences might come down to believing that different amounts of or different types of details matter, and you might use a theory that ignores certain details that someone else thinks is really important. So some example of this is that different implementations of AI or AGI might have functional equivalence up to a point, but at some point we might notice that they do in fact have different, say, safety or governance related properties. So that would be one example how this matters. I think another thing that comes up, I'm not sure how much this comes up for all of you, but I think it might. There's sort of a debate between, you know, hardcore computationalism, where you say, well, we have theorems showing like universal computability and proofs that like anything in principle could be computed by this specific computer. And then there's other people sort of maybe coming more from like biologically inspired views on cognition, more embodied or inactive notions. And they will say, look, your abstract system is not enough to actually implement the sort of complex behavior we see in living beings. And I think that disagreement comes down to something like how much detail matters. Computationalism relies a lot on this like multiple realizability assumption. So namely, it doesn't really matter on what material basis, on what substrate a specific computation runs. Like the details of the render a certain computation, it is computationally equivalent. And someone who thinks maybe matter materiality, the low level detail matters more, might say something like, oh, it is actually more than like realize, but it is like constrained in some additional ways by, for example, materiality or the way material is structured or organized. And yeah, this is important because it gets you very different predictions about, for example, what sort of competence could an abstract system like an ML system implement. Cool. And next peculiarity, it's a bit mind-boggling in my mind. We'll see. So I claim there's a kind of strange inversion going on when we study artificial artifacts between the functional and the mechanistic. So to explain this briefly, in the domain of the natural, so the just typical natural sciences, the function of a system is understood as maybe viable post hoc description of that system. But it's not a mechanistic explanation of how the system came about. And the functional description is only viable insofar as it is the result of a continuous process of adaptation to the environment. So eyes have certain functions, or ears have certain functions, whatever other wings have certain functions. But importantly, evolution hasn't found wings because they're good at flying. Evolution has found wings for other reasons, namely sort of evolution gradient descent like processes. But even so, what this means is that you are maybe in some ways, it's fine for you to say birds have wings to fly, but this is importantly a post hoc description and not an actual explanation for why birds have wings. This relationship is actually reversed. Here, the function of an artifact is that which is antecedent, so that is which comes first, while the internal environment of the artifact, so it's low-level implementation details, is that which comes later. What I mean by this is that if I'm a designer, and I set out to build a watch which can tell me the time, I first conceive of the function. I'm first interested in this specific function telling the time, and it's only then that I start to be like, well, maybe this low-level implementation will do, maybe this other low-level implementation will do. There's a lot going on here, but I think this is a bit interesting to just notice for now. Yeah, so you end up asking a question, which is like explanatory primary here. Are these just two alternative ways of talking about it? One is more low level, one is more high level, but like, does it start to matter? The fourth peculiarity, which I think is what will come to be true, or like, sorry, is the question of what will come into existence a question of matter of fact? Is the sort of like one necessary answer to this question. And by what will come into existence, like I mean questions like, will AGI be implemented on a transformer architecture? Is the answer to this question a necessary answer, like a matter of fact, or is this a contingent feature? And this is a bit confusing because in the natural sciences, you would say this must be a necessary thing. In the domain of the artificial, it might be relevant for you. It might be pragmatically useful for you to acknowledge that it's not fully a matter of fact for the following reason. So there's consider these three notions of what is possible. And there is importantly sort of what is physically realistic, like what is physically possible, what is possible as it's constrained by the laws of physics. This is sort of the very sober, realist view of this determines what is possible. And I believe this is importantly true. In addition to that, we have things like to what extent is a certain paradigm technically, economically plausible? So to be able to implement this sort of paradigm, is this paradigm, are there two paradigms which can in principle achieve the same functionality, but one just is much more costly, given how the economics level here, which is something like policies, political opinion, social opinion, and can also come to sort of differentially affect what actually comes into being. And I'm not saying these are sort of like, these mean that these like things like end up conflicting with what is physically possible. But I think as someone sort of like inside of history, as someone who's like all of you, trying to do the science of what sort of AI systems we are going to build, from your point of view, these factors, and there's interesting feedback loops between these layers going on. What this also means is that there's a certain historicity to scientific activity, so like a path dependency. So our current beliefs, our current scientific frameworks and current scientific tools, as well as sort of like manufacturing capacities and like economic landscapes. Those things, by means of sort of like changing the differential investment that goes into different physically plausible paradigms, will in fact affect that which comes into existence. So rather than there being a already predetermined answer to that, rather than there being already a predetermined answer as to which will be the most successful paradigm for building AGI, a scientist must understand their own scientific activity as being a part of like an iterative and path-dependent epistemic process towards which paradigms will come into existence. And why is this relevant? Well, it is relevant if you believe that different technological paradigms we could be choosing have different safety properties. And like now you maybe become interested in differentially affecting this, or at least in understanding your role in this embedded process. And this is why I call this the problem of paradigm choice, to sort of make a little bit of a pun on the notion of paradigm change, which is Kuhn has like introduced this notion in philosophy of science. Most of you are familiar with this. So he talks about, paradigms changing. I'm sort of suggesting, hey, there is actually a level of choice involved, which paradigms are being pursued, which can end up determining some of the features of reality as we'll come to meet it. So in short, the scientists theorizing effects which will come into existence. And this is importantly a philosophy of science that is trying to be a philosophy of science useful for the scientists actually doing the science. So like it is a philosophy of science from the point of view of the scientists rather than a philosophy of science sort of from a like perspective of nowhere, which I think how philosophy of science is usually handling. So like if obviously you zoom out to some point of view of nowhere, there is a fully determined answer to that which comes into existence, but this is kind of just not relevant to us bounded agents that are part of this process as it is at the moment. Cool. I'm done with this section. I think this is a section that's pretty dense. I don't think everything lands. I don't necessarily expect everything landed, but if there are confusions or questions, I'm happy to take them out. And else I'll go to the last section, which will involve a little bit more hot takes from my end, concrete hot takes.
I'm curious to get to the hot takes, but just curious if you see there as, I don't know, being kind of engagement with these challenges when you talk about kind of multiple realizations of technical systems, for example. I feel like this is maybe under discussed in alignment. People really like to kind of have their preferred way to AGI just be sort of necessary. And I don't know if you feel that, I don't know, if there should be kind of more direct reckoning with these than there are, and maybe what some causes are of people kind of not necessarily tackling these issues head on, which are important.
I don't think I have great answers as to like why it's not more discussed. Like I'm not sure how surprised I am about it. I think in scientific communities in general, like people are not very careful with terms a lot of the time, and it's like it's a hard thing to do. I think I'm definitely very unhappy with how terms like AGI are being thrown around. I think there's a typical way in which we sort of all agree, and it's like somewhat common knowledge with how we're unhappy about the term AGI being used, namely just like fairly different operationalizations. Is it like just basically God equivalence, or is it just sort of like transformative, various sort of problems there, just better on all tasks than like an average human, better on all tasks than like the best human, etc. So like this is a thing you can already solve with operationalization. But I think the thing I'm trying to point at with the multiple realizability goes beyond that, and I definitely think that is under discussed. And I think this like notion of AGI or even AI being a functional equivalence, like I think currently in general discourse, the field of AI just refers to the field of machine learning with like a little bit of like, oh yeah, we do remember we had like good old-fashioned AI at some point, but that's sort of not relevant anymore. But like this sort of mix up of like specific technological paradigm and like sort of a functional equivalence that we are interested in implementing, I think matters and confuses conversation to some extent, also confuses conversations between the ML community relative to other fields that have things to say about intelligent behavior, whether that's informed from sort of like cognitive sciences, biological sciences. So I think that makes the like transfer of insight, or even just like the like osmosis of ideas. This is like one obstacle, I think, to the osmosis of ideas there, which I think is like in expectation, definitely a harmful thing. So I don't think I have like particularly useful answer, but yeah, some thoughts. Cool. Okay, on to the last bit. The last bit is called How to Do Reductionism Well. Importantly, the first thing I want to flag, this is not an anti-reductionist rant. I am pro-reductionism in general, mostly because the world is too complex to understand it. It's in full complexity. So I think there is some like sophisticated notion of reductionism that is in fact very much appropriate in science making. But what I'm saying is doing reductionism well is a pretty intricate enterprise. And this is not going to be a full treatment of like, here is all the ways you could do reductionism well and what you should do instead at all. I think I'm going to point out exactly sort of 1, 2, 3 ways in which I have observed reductionism not being done well, according, at least in my books. The first thing I want to point at is what I'm going to call the myth of the intrinsic property. By that, I mean, we often ask, I think we often ask something like, is this model safe? Is this model deceptive? Is this model aligned? This is sort of questions I think we as in like alignment researchers are actually often explicitly or implicitly like actually the thing we're sort of trying to get at. What is happening here is that this question implicitly assumes that things like safety, deceptiveness, alignment, various other like safety, governance, etc., like risk-related, capability-related properties, we are assuming that those are intrinsic properties to the model. We're assuming that there's sort of like an answer to, does model X, does GPT-4 in isolation have this competence, capacity or not? Is it deceptive or not? Is it aligned or not? And what I'm trying to say is that this is like fundamentally an underdefined, underspecified, or like a wrong way to ask this question, because all of those things, safety, deceptiveness, alignment, various other things you can plug in here, I'm going to claim they are importantly relational properties. So treating them as intrinsic properties undermines, underdetermines, or like, sorry, intrinsic properties about the models which exist, ways in which it is like built, features that it has, like those intrinsic properties, however underdetermined a model's capabilities or risks, for example. One example here, I think this will be intuitive to some people and maybe not have that much power, but if I ask you for a given human in isolation, are they dangerous? I think this is an odd question. Because whether or not they're dangerous depends on various things. It depends on what tools they have access to. It depends on what environment they're in. Are they, like someone might be a very kind person in general, but maybe they can be treated badly to an extent that they would end up being. So like, I'm just gesturing at the question of like model X, system X in isolation. Does it have this thing, which is in essence a relational property? You can't answer this correctly. Why is this happening, or like what? And I'm now claiming there's like a reductionist bias going on here. One reductionist bias that is going on here is that if you are interested in the relational property, but you treat it as if it was a no matter I misspelled this or a lower order relational property, you will miss being able to identify it. Okay, so here's a citation that will hopefully help. So Wimstead writes, if the property is a function of the system's properties and the environment's properties, Keeping the environment constant will make the property look as if it was a function only of the system property. For example, fitness, in the evolutionary context, is a relational property between an organism and an environment. Keeping the environment constant makes it look as if fitness can be treated as a monadic property of the organism. Context dependencies are hidden in this fashion. So, cool. Like, let me try to reiterate this point. Whether an AI system is aligned or not is really cashes out in what this, how this alignment, how this model or how this AI system ends up behaving in the world that is deployed. And before you deploy the system, like, there is no meaningful notion of alignment, because alignment, the notion of alignment intrinsically is about also the context that is deployed in. This is true for safety as well. I'm also claiming this is true for deceptiveness. There are some narrow version of a fully internalist notion of deceptiveness. So, for example, when you limit deceptiveness as being the sort of thing where you have a model, it has a belief state, which is the thing it actually believes about the world, and it has this like other representation, and it chooses to strategically communicate this other representation knowingly. Yeah, this is like a fully internalist notion of deception. And importantly, I claim this is not all we care about when we care about deception. There's ways in which models can come to be deceptive without it being particularly meaningful to say they know the true answer, but they intentionally did not do that. I think we can have much more simple systems, which we might want to describe in these intentional terms, that can already do something that we would say has deceptive effects. And we might also be interested in deception that isn't like, I think like in the terms of like caring about safety and risks, it doesn't really eventually matter whether how much the system intended to do this. What matters is the effects on the world. Have people processes been importantly skewed in their understanding of their assumptions about what is actually true, such that like bad things occur from that. And this broader notion of deception you can't capture when you just look at the inside of the system. There's a second bias that I think is also interesting to point out, which is something like systematically, like there's something going on when we do reductionism, but not being careful about it, where we systematically favor sort of complexifying or adding on complexity to intrasystemic explanations. So again, I think the citation here should make this clear. When setting out to improve a simple model of the behavior of a system and its environment, and we have currently a description of a system and an environment and its behavior, but we want to improve this model. For example, because a number of simplifications will have been made, both internal and external to the system, there will always be room for improving the model's prediction by improving the internal description or analysis. So by complexifying what we assume or the theory we have about the internals of the system. In effect, the strategy involves the following working maxim. If a model fails to work or predict adequately, it must be because of oversimplification in the description of the internal structure, not because of oversimplification of description in the external structure. And so I think this is like what I'm kind of suggesting is like, no one here fully believes that the environment doesn't matter at all. But the way we do reductionism, and this is not just because we're like a bit dumb about it, like these phenomena are truly complex, and trying to make progress on understanding complex systems, we need to do some reductionism because it's hard otherwise. But what starts to happen is that you try to make your life easier, but just being like, well, there's lots of variables going on here. Let's at least keep some of these variables fixed. Let's fix the environmental variable. And now you like theorize, you make some prediction, and you notice, it's not quite fitting. The prediction isn't quite fitting the actually observed behavior. Let's adjust our theorizing. Let's like complexify our models a bit to adjust for the divergence. And now you're also biased to like always complexify your theory about the inner workings of the system while you still keep the environment fixed. And when you forget that that's what you're doing, what you end up with is kind of like later on interpreting your results as being like, wow, really seems like all that's going on here is like a bunch of complexity in the system, like, or produced by the system. But like you forgot that you were just holding the environment constant. So like obviously you can't be detecting anything about the relational property. Cool. So this is the rough idea of how we can do reductionism wrong to misunderstand complex behaviors that are like importantly relational. Why is this important? And now I'm gonna be a bit more bold and speculative and spicy, but I think that's maybe interesting. I'm also happy to get disagreement here. But here are some implications for interpretability and eval type work. So if you assume that model behavior is underdetermined by its internal features, then something important about the sort of theory of change of interpretability has been undermined or maybe just limited. So at the very least, so what I'm saying is something like mechanistic interpretability looks at the models and try to understand, like looks inside of the model and tries to understand things about inside of the model. And maybe we come to learn things like features that the model has. So for example, we come to learn that there's a thing like attention heads. That's cool. But importantly, I claim that there's additional theory needed to understand how an intrinsic feature of a model that it might have developed over training, how that connects up with high-level capabilities that we're eventually interested in. It is very non-obvious, and I claim interpretability alone can just not get you to how certain internal features of a model will or will not end up producing deceptive behavior, for example. And like this, this at least weakens, I think, some cases that have been made for interpretability and eval, and at least suggests something like you additionally have to do a bunch of theory, a bunch of like actual theoretic understanding for example, how intrinsic features might add up or like might link to high-level capabilities. Another example of this is that the relationship between model architecture and deployment context might be interesting, and we need to have theories about this. So for example, we can study an LLM system in isolation, but we might also be interested in studying sort of scaffolded LLM systems, like LLMs that sort of get access to additional tools, or LLMs that, or like several AI type systems, LLMs, or also others that start to interact with each other. There's a paper called Mindstorm, which like has various constellations of putting different multiple LLMs or AI systems in a specific protocol of interaction, and then being interested in the like emergent behavior of this sort of group actor. And like, again, like just by understanding the individual model doesn't mean we necessarily understand already enough about what emergent behavior we'll get from interacting agents. Prompt engineering, I think, is another really great example for how understanding the model on its own importantly underdetermines what capability we might be able to elicit from it. So in one sentence, the thing I'm kind of trying to say is that properties of a model, the right way you to talk about this would be that you can claim that you can make claims about a model X has a certain property across an environmental distribution, across a certain context, but a model X will never have a property sort of in isolation. Or like, so if you would just say model X has property Y, you would be saying that across any possible deployment context, it would have this property, which like in theory is not impossible. But like, I think this is like clearly not that the sort of thing we're able to say. We might be able to be precise when we would say something like across these environmental distributions, the model has this property. One more thing I want to say here, and I sort of alluded to this already, there's sort of a notion here of like, the sort of interpretability we're doing is looking into the model, so zooming in to the model and trying to understand its behavior about that. There might be another sort of, I'm a bit misusing the term interpretability now, but like, what if we do sort of like zooming out interpretability, namely sort of trying to develop a principal understanding of what capabilities and risks emerge when we get agents to interact, LLM systems or other types of AI agents. I think this is a really important question. I also think this is a really deeply difficult question methodologically, and I'll say a few more things about this. I've said in the beginning that I'm running just like PIPS program, and we're currently running a summer fellowship, and I have like a handful of fellows trying to like start to make progress on these questions. And I think there's some like really interesting observations, just like really how hard methodologically it is to even just guess at like what would it mean to gain a principled understanding about this. But I think it's like, given where we are at the moment, worth trying. But I think we're not yet there trying like really understanding what how to say principled things about this, or whether it's possible. So yeah, why care? I think some of the things I said can have effects on how you think about the theory of change of interpretability and evaluations. It might, for some users, it might totally undermine it. For others users, it might not totally undermine it. But yeah, if your theory of change goes via like, it allows us to predict features of future systems, or via like the value of eval. I think there's like things in here to update on. Maybe more importantly, no, actually not more importantly, but also very importantly, it's also just like a call for methodological rigor and also like good collective epistemics. What I'm not necessarily saying is that like various bits of interpretability research hasn't been useful at all. But I think we need to be really careful about interpreting the results and like importantly not over-interpreting them. And I think we're like very much currently are in a context where we tend to over-interpret the strength of results from interpretability research. And often I think they're able to say some things, but like much more limited things than we say. So for example, things about features that the system has developed, but that doesn't constrain our understanding of high level capabilities that much really. For reference, there's also, most of you might be aware of this, but the post against almost every theory of impact of interpretability has resonance with like a couple of things I've been saying here as well. Yeah, quickly, I was alluding to this already, like methodological challenges in studying LLMs, I think is really interesting. So like my high level perspective on this is something like, this is like just basically an entirely novel sort of like scientific endeavor, and the scientific community so far is like still very confused. There's like basically has been no time or very little time so far in like developing or converging towards like good practices and like what does it mean to like do some study on like LLMs, whether that's like looking into them or like looking at how they interact, that is like methodologically rigorous or at least methodologically well done, such that we feel like we have some confidence in the insights. To some extent, I'm like, this is like extremely understandable because this thing has really just emerged and we're still trying out. And I don't want to dissuade anyone from being like, whoa, I do want to run experiments here. I'm not claiming that these experiments are like particularly right now, but like one way of making progress on developing better methodology is by trying stuff and like noticing, oh, actually, I thought I disproved this hypothesis, but I clearly did not because I didn't consider all these additional auxiliary assumptions I've helped myself too. But this is like, as long as it is an iterative process to hopefully improve methodology, this is fine. But also the state of the art here is like really, really confused. Here's just one reason I think this is very hard. Let's ask for a second what sort of epistemic object LLMs are even. And I think there's like at least sort of 3 levels of explanations, which like are in different contexts really relevant. And there's a confusing question about how they relate to each other. And depending on what level of explanation you choose, you will interpret the results you get very differently. So in one sense, LLMs are designed artifacts. Like at some point, there have been ML engineers that have built this thing and they have built it with specific things in mind. And this sort of functional explanation or functional perspectives gives us some predictive power over what LLMs do. Pretty limited actually in this case, because like it's a sufficiently complex artifact by now. Another thing that is true about LLMs to some extent is that they're the product of a training process. So there is like very sort of like evolutionary or like explanations that do, or like claims that do hold or like have constrained what this thing has come to be. And another level of explanation is the sort of like imitative simulator type understanding. Like I can like look at an LLM, interact with it, and the one way of interpreting what it is doing is through this lens of like simulator theory or like just various notions of how it's like predicting over like what context it's in, what next words make sense here. And given these sort of like layered explanations of like what an LLM even is, I think it makes it very hard to like have good experimental design and have like robust interpretations of our results. And like, I think another thing that's going on, I've already alluded to this a little bit, the scientific method always relies on auxiliary assumptions. So like you are usually proposing a hypothesis, and then you say, if I observe this and this in this context, I can, and this doesn't occur, I've disconfirmed my hypothesis. That's like nice and good. But what is also true is that it's not just the hypothesis and some other premises. There's a bunch of auxiliary assumptions that we're always helping ourselves to. And what I'm trying to point at is that I think it's just like the list of auxiliary assumptions in the case of trying to understand LLMs or interacting LLMs is very long, and we're not very confident about most of these auxiliary assumptions. And I want to illustrate this by analogy. So like, I think in physics, this is true as well, the role of auxiliary assumptions. Like you make a physics experiment, and one auxiliary assumption that you make use of is that you assume that the measurement tools you're using function well. If this is not in fact true, like your deductive reasoning about whether your hypothesis has been confirmed or disconfirmed isn't valid anymore. But it's you know, like, but we can be relatively confident whether or not the measurement tool worked. And yet there were already causes some problems. But psychology is even harder, right? When we make psychology experiments, definitely a much more fraught field. And one of the reasons why we're not getting very robust results there is that there's lots of auxiliary assumptions going in. What I'm claiming is something like, I think psychology is maybe even still better off than LLMs. I'm leaning in this a bit. I think there's some reasons for why it's not, but the problem is something like a bunch of the assumptions we make when we try to study other humans, the assumptions we will make are actually informed by us being the same type of mind to some extent. And what happens when we study LLMs is that sometimes we carry over those assumptions and might do something like, well, you know, this sort of like the simulacra sort of thing. It like probably reasons kind of like humans. And then sometimes this assumption will be kind of fair and sometimes it won't. And I think we understand very little about when that's the case. Or we might be like, whoa, I really should not assume anything anthropomorphic about LLMs. But then like, what assumptions are you like making use of instead? So I think that's one of the reasons why it's a wild west, in my opinion, currently in understanding LLMs, in particularly LLMs interacting with each other and how to interpret results there. Here's another implication from this like intrinsic property myth that I talked about, namely in our very understanding of what we should think about, what this like notion of alignment even points at. Two examples simply is like, one is like, should alignment solutions be robust to scaling up? So like, I'm reading, for example, Andrew Critch's robust agent agnostic processes. This is sort of what multipolar failure looks like post, as a critique of saying single intent alignment. If that's what you think alignment is, this will like fail in these ways. And if you want alignment to mean not to fail in these ways, single intent alignment doesn't scale up to like multi-agent settings robustly. So that's how I'm trying to like use the notion of robustly scaling up here. So we can like so and this might be an example of, we thought this is like an intrinsic as sort of a property limited to interactions between a single human and a single AI system, but actually we have been holding constant or ignoring these other features about the wider deployment context that make it such that this actually does not generalize. Another one, I'm just gonna sort of tease at this because this is a big box worm of what is it, box of worms or something like that. Anyway, so I think implicitly or explicitly a lot of alignment proposals assume that values are intrinsic properties of humans in some shape or form. And if this assumption is not true, and I believe it's not true, I don't think all of my values, whatever those are well described by being like they're somewhere represented inside of me. If this assumption is not true, but our alignment proposal relies on this assumption, it will also not generalize or be robust to ways in which like things that I want to refer to as my values or things I care about in some broader notion are not captured. Cool. For the sake of time, I think I have. Perfect. Wow. Okay, cool. Yeah, so okay, that's basically it. This is like a maximally short summary. Problem 1, part 1, I try to gesture at something like there's problems of epistemic underdetermination. One way of making robust progress, like making sort of systematic progress despite underdetermination, is to seek robustness, epistemic robustness through triangulation. That's sort of the essence, I think, of that part. The essence of the second part, a bit harder to summarize, but I want to point at there is epistemic peculiarities that come with trying to study as well as engineer designed artifacts, and like gesture at some of the weirdness that comes with that. And the third one is that in the context of studying complex phenomena, in particular relational phenomena or properties, this is what I've mostly been talking about, but there's also other things that would sort of fall in this bucket. In those contexts, doing reductionism well is intricate and hard, and sometimes we might do it badly, and then our insights won't be genuine insights. Okay, that's it. I have like some references that I've used in the talk, but that's basically it. And I'm happy to discuss or take questions.
I have a question, though I'm not totally sure how to word it yet. You were describing the how scientists should have visibility in the sort of like embedded system that they're in, of the like what is possible and what should be created and etc. Do you have any insight on how to get visibility on that from the inside of that system, and like what sorts of levers one should be on the lookout for?
Yeah. So I think this is like a pretty tricky point, and inferring very concrete action steps from it is not trivial. And I like a bit want to apologize for like suggesting the thing without it maybe being like very easy to point at concrete relevance. I do think it's relevant, which is why I decided to say it anyway. But anyway, so I think there's like two things I want to point out here. When I say something like there's a historicity or a social embeddedness, and there's an interesting thing of like being inside of this process as someone engaged in the science or the engineering of it. I think there's two things. I want to say something about the sort of like backward looking aspect of this and the forward looking aspect. You ask about the visibility. I think there's not that much to say about it, so I'm going to also say the backward thing because I think it's important. One implication of this is that also the place you are currently standing, and like where the field is currently standing, and the way the field talks about the systems and like the theories that exist, they importantly are the product themselves of an epistemic history or like a history of ideas. And I think it is very valuable for a epistemic community to spend some of its resources of being somewhat self-aware of where your notions come from. There's no need in overdoing this either. Like, I'm not saying this is like all we should be doing. But I think it matters. So like traditionally, like in the case of AI alignment or like the AI domain, we are pouring a lot of notions from like microeconomics, game theories. The sort of like intellectual history means that we have been getting our vocabulary from these domains. And these domains have really interesting things to say, but these domains are taking certain lenses and understand certain phenomena and are less well placed to understand other phenomena. And it can be hard to bring in other perspectives because other intellectual perspectives or schools of thought partly use different language, which makes there sort of like this, there being a certain barrier and the certain like need for actually epistemic translation between them in the first place. And I think that's like a larger explanation for why there's less of this than is needed. But being even just self-aware of like where your ideas and priors and beliefs come from feels important to do this like error metabolism or self-correction well. Which is also sort of one of the founding ideas for like PIPs, where I'm like, ooh, there is more traditions that have interesting things to say, and they're currently not having an easy time coming into the discourse. Let's make it easier for those to come in. So that's the backward-looking part, which I think is actually already important for the forward-looking thing as well, because it shapes your interpretation of what might be possible and how. How to gain more visibility? So I think one is through the triangulation and robustness. So the claim here would be, if you're only using your singular epistemic lens to predict what is going to happen, I don't think you're in a great position epistemically to have reliable predictions for what will happen. So if you help yourself to more perspectives, you will have a better understanding of the space of possible things, as well as which of those seem like sort of more necessary and which ones seem much more contingent. And once you know which ones are more contingent or not, you can steer away or towards them with more force, right? If there's like, what would be a good example? So like one practical question, I've in the past at some point talked to someone who was like, look, I'm not that interested in studying neural nets. I'm like interested in other methods, but I also want to like help with this alignment problem, and I'm currently kind of assuming like the powerful systems we are worried about will be implemented on neural nets, so I basically should be studying this thing, but maybe I even believe this other paradigm has like better safety properties. I think I don't have a good answer for what you should do at this point, but I think it's important to notice at this point it is not necessarily overdetermined what AGI will look like, and people working on different paradigms will affect what AGI will look like. So if you believe a certain paradigm has better safety properties, a valid strategy is to be like, let's make this paradigm more visible, more tractable, more promising, because like I think that can, in this like differential or contingent history, have an effect. So like that would be sort of one example. I think that concretes here are tricky, but I think it's important for like people in the field to at least have that perspective. Yeah.
That makes sense. Thanks. Okay, it doesn't seem like anybody else has any questions. That was a really wonderful talk. Thank you.
Thanks. Cool. Thank you so much. Bye to everyone.
Bye.